right? Okay, so diagram 8.1, right, shows a box, okay, filled with ice and fish, okay. So the ice are used to keep the fish fresh, okay. So the fishes are, and the ice are in the thermal equilibrium, okay. So, okay, so what is a thermal equilibrium? Okay, so thermal equilibrium, so remember three sentences that I have told you before. Okay, so the first one, the temperature between two objects is same. Okay, rate of heat transfer between two objects is same. Okay, or equal. And then another one is the net rate of heat transfer between two objects is 0. Okay, so that's the meaning of the thermal equilibrium. Okay, so you can just put one of those three I already gave. Okay, so this is the answer, right? So the temperature of two objects is same, and the rate of heat transfer between two objects is same. Okay, all right. So we go to the next slide. Okay, so diagram 8.2 shows the ice melted after a while. Okay, so explain why the ice melt. Okay, so this one is of course if ice melting, so means this one is a latent heat of fusion, right? So latent heat of fusion. So why the ice melt? So of course the heat, okay, will be absorbed by ice, okay, from the surrounding. Okay, and then the heat will be used to overcome the attraction of the molecule to change from solid to liquid, right? So this one is actually the latent heat of fusion. Okay, latent heat of fusion. Okay, vaporization, that one is from liquid to gas or gas to liquid, right? Okay, so we move to the next slide. Okay, so the mass of ice which have melted are 12.5 kg, and the specific latent heat of fusion is 3.3 times 10 power of 5. Okay, so asking you to find the heat absorbed by the ice. Okay, so this one, because this specific latent heat of fusion, so mean we have to use the formula Q is equals to ml. Okay, so Q is actually the quantity of heat that need to that need by the ice, okay, to convert from the solid to liquid. Okay, so the M is 12.5. Okay, and then the L already given here, right? 3.3 times 10 power of 5. Okay, so just use your calculators. You got 4.125. 4.125 times 10 power of 6 joule. Okay, so this is the answer. Okay, all right, the next one. Okay, so diagram 8.3, right, shows the method used in the fresh fish export industry. Okay, so table 8 shows several characteristics of different boxes and ways which can be used to enable the fish are kept fresh for a longer time. Okay, so this is the method KLMN. So the type of material, whether you want to use the styrofoam or wood, and the thickness, whether it's thick or thin, and the type of material to wrap the fish, whether you want to use a plastic or aluminium foil. So remember, okay, for this question, right, this is section A, I think. Okay, so question number 8. Let's see, my laptop is hang again. Okay, so it's okay. We just continue, right, while waiting for my laptop. Okay, so this one asking you to find the type of the material for the box. Okay, so this one you have to use the styrofoam. Okay, so because styrofoam is a good insulator, okay, good insulator, and it also can prevent the heat from loss to the surrounding. Okay. Mm, sorry for the. Okay, and then the next one is the thickness. Okay, the thickness of the wall of the box. So should be thick. Okay, so this one to prevent the heat loss to the surrounding. Okay, and then the type of material to wrap the fish. Okay, so this one should be aluminium foil. Okay, should be aluminium foil. Okay, so you can say good heat insulator, or you can say to prevent the heat loss. Okay, okay, so this one you have to choose M. So for number 4, the answer should be M, right? Good. You can see here my voice, right? I don't know what happened to my laptop. Wait. Okay, it's okay because you already got the books, right? The hard copy, so we can just continue. Okay, so page 91. Okay, page 91 is said diagram 8.1. Okay, alright. Uh, okay, so this is the answer. I think already record, right? Yeah, already record. Okay, sorry, wait, I refresh first. Okay, so we move on, right? So this one already explained to you, already discussed. Okay, so move on to the next slide. Okay, so diagram 8.1 shows a phenomenon of sea breeze at the seaside. So the phenomenon is due to the difference in the specific heat capacity. Okay, so at the land here, okay, the specific heat capacity is lower, right, compared to the sea. Okay, so what is the meaning of the specific heat capacity? Okay, so the amount of heat, right, the amount of heat required to increase 1 degree Celsius for 1 kg of substance. Okay, so this is the meaning of the specific heat capacity. Alright, and then next one, okay, next one, so indicate the arrows, or indicate with arrows, right, the direction of motion of warm air and also a cool air in the diagram 8.1. Okay, so this one because the land has a low specific heat capacity. Okay, so means it will be heat up faster compared to the sea, right? So the hot air is actually the density is low, right? So the hot air will go upward. Okay, hot air will go upward. Okay, and then the cool air from the sea, okay, we go to the land. Okay, so asking you to mark the direction. So this is the direction. Okay, okay. There's the answer for question number 8A and also B. Alright. And then this one asking you to explain the phenomenon of sea breeze. Okay. So the first one I have to say the specific heat capacity of land is lower. Okay. The air near the land heat up faster. Okay. And because of the density of the hot air is lower. Okay. So it will rise up. Okay. And then the cold air from the sea will go to the length. Okay, so like the one that I already draw. Okay, right, next one, we move to the next slide. Uh, Sorry class, I don't know what happened to my laptop, right? Okay, can we just move on for number 92, right? While waiting for my laptop. Okay, now for D, right? So diagram 8.2 shows a thermos flask. Okay, so that table 8 show three types of thermoflask and their characteristic. Okay, alright. And then the first one, okay, for the stopper, okay, for the stopper should be hollow plastic. Okay, because this one to prevent the heat loss to the surrounding. Okay, because air is actually a very good insulator, right? And then number two, double wall tube should be glass. Okay, so good insulator, right? And then next one, okay, the space between the double wall is vacuum, right? So there is no medium for heat to transfer to the surrounding. Okay, and then based on diagram in 8D, determine which thermostat is the most suitable to maintain the temperature of hot drink for a long time. So the answer should be Q. Okay, so the answer should be Q. So hollow plastic, glass, and also vacuum. Alright, next one, number two. Okay, so diagram two shows a mercury thermometer which has not calibrated. Okay, so state the physical change in the mercury when the temperature increase. So when the temperature increase, the mercury will be expand. Okay, so mean when you expand, the volume of the mercury will be increased. Okay, so the first one, the answer is volume of mercury. Okay, and then the second one asking you why is the mercury used in thermometer? Okay, so the answer should be easy to expand and contract. Also, it's not stick. Okay, mercury is not will not be stick. Okay, on the glass. Okay, so that's the reason. All right, and then next one. Okay, so the length of the mercury column in the thermometer 8 cm at 0 degrees Celsius and 20 cm at 100 degrees Celsius. Okay, so what is the difference in the length of the mercury column at 0 degrees Celsius and 100 degrees Celsius? So this one you just minus, right? 20 minus 8. So you got 12 cm. Okay, so this is the first one, the first answer. Okay, and then the second one, okay, when the thermometer is placed in liquid X, so the length of the mercury column is 5 cm. So calculate the temperature of liquid X. So this one you have to use this formula, L theta minus L0, right, divide by L100 minus L0, okay, times 100, okay. So what is L theta? Okay, so L theta is the length of the mercury. Okay, the for the temperature that you want to find. Okay, for the temperature that you want to find. So let's say this one, the length of mercury is 5 cm, right? So you need to find the temperature of liquid X when the mercury is 5 cm. The length of the mercury is 5 cm. So means the L theta is 5 cm, right? So 5 minus, so L0 is the length of mercury, okay, when it's at 0 degrees Celsius or when it's melting, okay. Sometimes they didn't say that at 0 degrees Celsius. Sometimes they say at melting point. Okay, so it means that one is L0. Okay, sometimes they just put melting. Right, melting point. So you have to know a melting point is 0 degrees Celsius for water. Right? Okay, and then 5, right, minus 8. Right? And then L100 is actually when the length of mercury when the temperature is 100 degrees Celsius or at the boiling point. Okay, so sometimes they didn't put 100 degrees Celsius, they just put boiling point. So boiling point for water is actually 100 degrees Celsius, right? So this one you have to know. Okay, so L100 is 20. Alright, L0 we already know that is 8. Okay, and then just time by 100. Okay, so you got 25 degree Celsius. Okay, so this is the answer. No, not 35. Sorry. I think negative, right? Negative 25. Yeah, negative 25. Okay, because so the negative 25 plus 5 minus 8 is negative 3, right? Okay, so the answer should be negative 35 degree Celsius. Okay, so next one. Okay, what does it mean by specific latent heat of vaporization? So latent heat means there is no change of temperature. Okay, so remember the graph, right? So the graph, okay, should be like this, right? So for this one, okay, when the temperature is not increased, so this is solid first. Okay, solid plus liquid. Okay, and this one is liquid. This one is liquid plus gas. And this one is gas. Okay, so specific latent heat and vaporization. Latent heat means there is no change of temperature. So whether this part or this part, right? So for this part, solid to liquid, we call it as a latent heat of fusion. And this part, liquid to gas, okay, we call it as specific latent heat of vaporization. Okay, for this part, okay, if you want to calculate the quantity of heat, you use MC theta. This one you use ML. This one is MC theta again. So this one is still ML and this one is MC theta. Okay, so this is the formula. Okay, if you want to calculate the quantity of heat for each phase. Okay, so for this one, asking you the meaning of specific latent heat of vaporization. Okay. Alright, so the amount of heat required to change liquid to gas or vice versa without change of temperature for 1 kg substance, okay? Because you have the word the specific there, so you need to put 1 kg here, okay? Alright, for number 2, okay, so explain why ice cubes stick to the wet finger, not to dry finger, okay? So the first one is the water in the finger, okay, the water in the finger, alright, so they contain the heat, okay. So when it touch the ice there, okay, the heat will be released from water, okay, to the ice, okay. So the heat will be released from the water to the ice, okay, and then the water will change to the solid, okay. Since the heat will release, okay, so the water will change to solid, okay, that means ice, right? So the amount of heat required to change liquid to solid is called as a latent heat of fusion. Okay, so the water in because the finger is wet, so that means there is a water, okay, on the fingers there. So they contain a heat there, right? So when it touch the ice, so the water there will release the heat, right? Will release to the heat. Will release the heat. So now the water on the finger it will become ice. So that's why it stick to the ice. Okay. So the amount of heat required to change the liquid to solid is called as a latent heat of fusion. Okay. So that is the answer for this one. Alright. Okay, next one is the calculation. Okay, so determine the melting point of the substance. Okay, so this one the answer is 77. Okay, this one. 77. Okay, so label first, this is solid plus liquid, okay, and then this one is liquid. Okay, so the answer is 77 degree Celsius. Okay. Okay, next one asking you to calculate the specific heat capacity, okay, for the solid substance. Okay, so the first one you have to use, okay, you have to know what's the information that's given. Okay, so the solid substance of mass, okay, already given you the M here, okay, of mass of 0.5 kg is heated using an emission heater of 240 volt 50 watt. Okay, means giving you power here. Okay, and then diagram 11.1 shows a heating curve of the substance. Okay, so determine this one we already answer. Okay, calculate the specific heat capacity of the solid substance. So solid is actually at this phase, right? Okay, so means we have to use this area. Okay, okay, and then what is the formula we have to use? Since they already give the power here, right? So we assume that the electrical energy is actually equals to the quantity heat of energy. So means the formula for electrical energy is P T. So this is the formula for the electrical energy. So electrical energy is equals to the quantity of heat, okay, which is MC theta. So this is the formula. MC theta is equals to Q, right? So Q is actually quantity of heat. Okay, so we assume all the electrical energy that been provided by the emission heater is actually used, okay, to convert it to the heat energy. Okay, so P is actually 50, right? And then the time must be in second. Okay, so this one in minute, right? So change to seconds mean 3 times 60. So you got 180 here. Okay, and then the mass is 0.5. Okay, and C you need to find. Alright, theta is the change of temperature. Okay, so means 77 minus 32. Okay, so you got 45 here. Okay, so change of temperature, just minus 77 plus 32. Okay, final temperature minus initial temperature. Alright, so use your calculator. So you got C is 400. Okay, so the unit is JkG -1 degree Celsius -1. Okay, so this is the unit for, this is the answer for C. For C for number 2 here. Right? Okay, number 3. Alright, calculate the value of T if the specific latent heat of fusion of the substance is 3 times 10 power of 4. Okay, so T is here, right? So specific latent heat of fusion means this one solid change to liquid or liquid change to solid. Okay, so means this area, right? This area. Okay, so for this one, okay, you have to use what formula? Okay, again, we use PT, right? Electrical energy. Okay, PT is equals to, but for this time, okay, since we use this part, right? This part, so I already told you before, if this part is MC theta, for this part is actually the quantity of heat is Q is equal to ML, right? So for this part, we use PT is equals to ML, right? Okay, the power here is 50. Okay, the time is actually T minus 3. Okay, because we only want to find for this area. So the difference time here is T minus 3. Okay, 3 minus 3. Okay, but this one you have to change to second. So T minus 180. Okay, T minus 180. Okay, again the mass is 0.5. Okay, and then the L is 3 times 10 power of 4. Okay, right, then you expand it. Okay, expand it. Okay, and then I got the T, the value of T is 8 minutes. Okay, it's actually 408, 400, no, 648 times 10, 60, 480, I think I got second. Okay, but this one, because they're in minutes, so I divide by 60, I got 8 minutes. Okay, so you have to give the answer in minutes because the axis here, the unit is in minutes. Okay, so the answer is 8 minutes. Okay, right, so this is for B3. Okay, PT is equals to ML. Alright. Okay, for the next slide, okay, So table 11.2. Okay. So table 11.2 shows the specification of four types of ice cream container. Okay. So asking you to find, okay, to choose, right? To choose which one determine the most suitable ice cream container that could be used in the to keep the ice cream in the solid state and portable. Okay, so you have to choose based on the characteristic given here. Okay, so the first one, okay, for the specific heat capacity, of course have to use the high specific heat capacity, so it's not easy to heat up, right? And then the container should be small size, right? Because they want the portable one, right? So must be a small size, so easy to handle. Okay, and then the container should be bright color. Okay, so heat reflector and PVC plastic container. Okay, so this one to reduce the heat loss to the surrounding. Okay, so for this question, remember you must do the table. Okay, and then don't forget to choose. Okay, and copy back all the characteristic that you choose. Okay, so this is the answer for the ice cream container here. Right. So the next one, okay, so diagram 7.1, okay, shows two cups, okay, of coffee of equal mass being cooled by adding a few pieces of ice cube. So initially each cup, okay, contains 0.2 kg of coffee at 75.5 degrees Celsius. Okay, so it is observed that both cups of coffee reach a final temperature of 35 degrees Celsius at the same time. Okay, so for A, the melting of ice involved the absorption of latent heat of fusion. So what is mean by specific latent heat of fusion? Okay, so this one amount of heat required, right, to change solid to liquid or vice versa, okay, for 1 kg of substance without change of temperature. Okay, so the keyword here is amount of heat, okay, change solid to liquid or vice versa, okay, 1 kg without change of temperature. So this is the keyword here, okay, for the meaning of the specific latent heat of fusion. Okay, for B1, which cup of coffee requires more ice? Okay, so of course B, because the ice being put alright outside the cup, right? This one inside the cup. For this one, they put outside the cup. Okay, so the answer is D. Okay, next one. So explain your answer in B1. Okay, because the ice is exposed to the surrounding. Okay, so the heat will be absorbed from surrounding. So the ice here will be melting, right? So means you need more ice, okay, to cool the coffee inside the cup here, right? Compared to this one, you put ice inside the cup. Okay, so this one will cool faster. Will cool faster than this one. Okay, for C, right, calculate the heat release when the coffee is cooled down to 25 degrees Celsius. Okay, so for this one, what info that they already give you? Okay, so they give you the mass here 0.2, okay, and the change of temperature is 75.5. The initial temperature is 75.5, okay, and then the final temperature is 25 degree Celsius. Okay, so for this one, you just use Q is equals to MC theta. Okay, so this one use Q is equals to MC theta, right? Because there is change in temperature, right, from 75.5 to 25. Okay, so means this one is specific heat capacity. If latent of heat means there is no change of temperature. So 0.2, okay, C is 4,500. Okay, and then this one is theta is the change of temperature means 75.5 minus 25. So you got 40.5. Okay, so the answer is 45,400 joule. Okay, so this one I put here is, you don't know, minus 25. Okay, change of temperature. Okay, so we move on to the next question. Okay, calculate the mass of ice needed to cool the coffee in a cup to 25 degrees Celsius. Okay, so this one they give you the specific heat capacity of water and also the specific latent heat of fusion of ice. Okay, so means if you know the graph, right? So for the ice to melt, okay, for the ice to melt, so let's say this is the graph. Okay, solid, solid plus liquid, liquid, liquid plus gas, and this one is gas. Okay, so ice, the first one is from solid, right? Solid, and then it will be transformed to the liquid, right? It will melting, it will melt and transform to liquid. Okay, so means, okay, at this point, okay, at this point, the ice is totally melt already. Means all of ice already changed to liquid. Okay, so means, okay, you have to use mc theta here, right? Remember the formula for this part is mc theta, and the formula for this part is ml. Okay, and asking you to find the mass of ice. Okay, so means you don't know the m here. Okay, so we use the formula mc theta plus ml. Okay, because we need to know, wow, how much the energy will be used, okay, from here to here, okay, until it melt, totally melt. So mc theta plus ml. Okay, so it's equals to, right, the one that we already answer. Okay, the value is 45,400. Okay. So mc theta, you don't know the m here, so I put mi, okay, mass of ice. C, the specific heat capacity for the ice is 4,200. Sorry, 3.36, right? 3.36. Let's see. No, correct. 4,200. Sorry. Okay, and then the theta is 50.5, I think. Okay, 50.5. Okay, and then plus m here is, you need to find what is the mass of ice here. And then the L here is 3.36 times 10 power of 5. Okay, so it's equals to 45,400. Okay, so try to solve it, right? So the answer should be M. Okay, mass of ice needed is 0.103 kg. Okay, just multiply that and then divide, right? Okay, got the value here, so just divide after that. So you got M is 0.103 kg. Okay, and then next one. Okay, so what is the assumption? So the assumption that you made is that no heat loss to the surrounding. Okay, so means that the amount of heat here, the amount of heat released when the coffee is cooled down is actually same as the amount of heat absorbed by the ice, right, to cool down the coffee. Okay, so that's the assumption. Okay, for this one, number 3, okay. So diagram 3 shows an apparatus to determine the specific latent heat of vaporization. So the electric heater with power 100 watt is used to boil the water in vacuum flask. So the steam produced condensed and the water is collected in the beaker under the glass tube. Okay, so what is meant by specific latent heat of vaporization? So amount of heat required to change liquid to gas or vice versa for 1 kg substance without change of temperature. So this one already discussed so many times. Okay, so this is the meaning. Alright, for the next one, so why they use a vacuum flask in this experiment? So we know vacuum means actually, if vacuum, okay, means there is no heat transferred, right, to the surrounding, okay. So there is no net heat transfer, sorry, there is no heat transfer to the surrounding, okay. Alright, for C1, okay, for C1, calculate the energy supplied by the heaters. Okay, so you know from the question they already give you the power, right? So energy supplied by the heater is actually the electrical energy. So we use the formula E is equals to PT. So the power is 100. Okay, and then the time given here already 500. So you got 50,000 joule. Okay, so this is the answer. Alright, next one. Okay, next one asking you to find based on the answer in 3C1, calculate the specific latent heat of vaporization. So we assume that all the electrical energy that being supplied is being used to change from liquid to gas. Okay, so the answer, the formula should be PT is equals to ml. So we assume that all the electrical energy, okay, being supplied, okay, is used to transfer, okay, all the liquid to gas. So mean this one is Q is actually from Q for equals to ml. Alright, so the power here already calculate, okay, so this one is 50,000, okay, so 50,000. So the M here is 0.2. Okay, and then you find the L, right? So the L is actually 2.5 times 10 power of 5 J um no, I forgot still. Wait. Mm, J kg negative 1. Right. Okay, so this is the answer. Okay, next one. Okay, so this one is diagram 11 shows the cross section of the pressure cooker. Okay, so the first question asking you to explain how the pressure cooker works. Okay, so this one is actually they use the gas law. Okay, so the gas law, pressure and temperature. So means this one they use the pressure law, right? So gas law got three gas law, right? Boyle's law, Charles law, pressure law. So for the pressure cooker they use the pressure law. Okay. Alright, and then the first one is the cooker is heat up. Okay, so means the temperature will increase. Okay, so for the constant value, the pressure in the cooker will also increase. Okay, so this one is because of the kinetic molecule energy, right? Kinetic energy for the molecule, okay, they increase. Okay, because the speed, the speed, the velocity of the molecule increase, so means the kinetic energy of the molecule will also increase. So means there will be more collision, right, between the molecules and also the container. So this one will increase the pressure, right? And then as the pressure increase, the boiling point will also increase, right? Because we know P is actually directly proportional to T. Okay, and then the food will cook faster. Okay, so what is the function, right? Okay, the next question asking you what is the function of the release valve. So this one is actually to release the pressure. Okay, the extra pressure, okay, extra high pressure inside the cooker. Alright, so that is the function of the release valve. Right. Okay, next one. Alright, table 11 shows the characteristic of the pressure cooker. Okay, so this one material base, material for the base, material used for the handle, thickness, and also the rusting effect. Right. Okay, so this is the choice. Okay, this is the answer. Okay, so you can choose from one from this answer, this reason. Okay, for the material for base, of course, it has a low specific heat capacity, and then also heat up faster. Okay, temperature increase faster, heat up easily, good heat conductor. So any of the answer can be accepted. Okay, and then the next one is a material for the handle should be wood, right? Because high specific capacity, not easy to heat up, temperature increases slower, does not heat up easily, and also good heat insulated. Okay, for the thickness should be high, okay, so it's stronger, okay, so can withstand high pressure and not broken in high pressure, okay. And the last one should be low rusting effect. So it does not rust easily or oxidize easily. Or you can put here is actually long lasting. Okay, long lasting also can. So low rusting effect. So the last one, of course, you have to choose. So I choose R. Okay, because of the copper base, wooden handle, high thickness, and also low rustic effect. Okay, so this is how you answer for question for the pressure cooker. Alright, so next one for D1. Okay, so this is the last question before I stop. Okay, so sketch the temperature time graph for the process of melting ice. Okay, so the question says 500 grams of ice at negative 3 degrees Celsius is put into a glass and left to melt to room temperature at 30 degrees Celsius. So you have to sketch the temperature time graph. So at this state is at negative 3 degrees Celsius. Okay, so you draw a graph here. Okay, since it start from negative 3, so should we start from here? Okay, so this one should be negative 3. Okay, and you know that ice will melt at 0 degrees Celsius. Okay, and then after that you will increase back. Okay, until here is 30 degrees Celsius. Okay, so this one is the temperature, degrees Celsius. This one is the time in second. Okay, so this is the graph. Okay, so this is the graph. Okay, for number 2. Okay, calculate the quantity of heat gain by the melting ice. So I already explained to you. Okay, so this one is actually solid, right? It's ice, solid. Okay, and this one is solid plus liquid. Okay, so starting from this point, all the ice is actually already melt to water. Okay, so what the formula will we use is MC theta and ML. Okay, so if you want to know, okay, what is the quantity energy that you need, okay, to melt the ice here, so you just add MC theta plus ML. Okay, so the formula should be MC theta plus ML. Okay, it's equals to Q here, quantity heat energy needed. Okay, and then the mass here already give you 500 gram, change to kg 0.5. Okay, 0.5. Okay, and then the C here is, okay, C is actually the specific heat capacity of ice. That means 2100. Okay, and then theta is the change of temperature, right? So negative 3, 0 to 0 means 3 degrees Celsius. Okay, plus, okay, M is actually the mass again, 0.5. Okay, and then the L is latent heat of fusion is 3.34 times 10 power of 5. Okay, so you just calculate, okay, just multiply. Okay, so I got the answer. Wait, I already calculated before. Okay, so the answer is 1.7 times 10 power of 5. 1.7 times 10 power of 5 joules. Okay, so this is the answer for question D2. Right? So I think I stop until here. Sorry for waiting me. Okay, and sorry for all the technical problem with my laptop. Okay, so thank you class. And the amount of heat absorbed. Uh, um, no need because Evan, you still here, right? No need because they only ask you how the amount of energy heat need to until the ice is totally melt, right? So until that point, if you add MC theta again, so mean that one is actually the energy need to rise the temperature from 0 to 30 degrees Celsius, correct? So the point that I already showed you before, right? So at that time they already changed totally back to they already changed totally to water, so no need. Okay, so that one is if you add MC theta, mean that one is actually to increase, right? To find the energy that need to increase the temperature. Okay, so no need. Okay, no need. Okay, thank you.